Consider a person who spins a large grindstone by placing her hand on its edge and exerting a force through part of a revolution as shown in the figure. A. How much work is done if she exerts a force of 200 Newton through a rotation of 1.00 radian? The force is kept perpendicular to the grindstone's 0.320 meter radius at the point of application, and the effects of friction are negligible. So we are given perpendicular force perpendicular to the radius at all times, that's equal to 200 newtons. And we are told that delta theta, or the rotational displacement, equals to 1 radian. What else do we know? R, the radius of the grindstone. That's equal to 0.32 meters. We are told that friction is negligible, meaning it's zero, so its effect is going to be zero. A is asking for the rotational work done. And the work done rotational is equal to net torque times delta theta. And the net torque is equal to a perpendicular times R and delta theta. Alright, so the force is 200 newtons. Radius of the grindstone is 0.32 meters. And the rotational displacement is equal to 1 radian. That will be the work done. That's equal to 64 joules. B. What is the final angular velocity if the grindstone has a mass of 85 kilograms? So mass of the grindstone is given. That's 85.0 kilograms. And what we are asked to find is omega F. And omega naught has to be 0 because it has to start from not moving, so from 0. Alright, so we don't have enough information to calculate omega F, but we have information to get the angular acceleration, and then we can go step 2 to find omega F. So what is the angular acceleration? The angular acceleration is net torque divided by moment of inertia. And we know that moment of inertia in this case is solid disk, and that is equal to 1 over 2 mr squared. 2 and tau net is equal to F perpendicular times R divided by mr squared. One of the R's go, we are left with twice the force divided by mass multiplied by R. So 2 times 200 Newton divided by the mass of the grindstone, which is 85.0 kilograms, multiplied by its radius, which is equal to 0.32. That's equal to 14.7 radian per second squared. So now we know the acceleration and we know the displacement, therefore we can calculate omega F. We know omega F squared is equal to omega naught squared plus 2 times alpha times delta theta. Therefore, omega F will be equal to square root of omega naught squared plus 2 alpha times delta theta. Plug in the numbers. Omega naught is 0 plus 2 times alpha, which we have calculated earlier, 14.7 radian per second squared, multiplied by delta theta, which is given to be 1 radian. That's equal to 5.42 radian per second. C. What is the final rotational kinetic energy? C is asking for kinetic energy rotational final. The kinetic energy rotational final is equal to half I omega F squared. Half into I, in this case is a disk, solid disk, the force is going to be 1 over 2 mass mr squared multiplied by omega F squared. Plug in the numbers. It's going to be 1 force times 85 kilograms multiplied by the r squared. R is 0.32 meters squared times omega F squared, 5.42 as calculated in B, radian per second. Everything squared. So kinetic energy rotational final is equal to (64 joule). And since the initial kinetic energy is 0, the change in kinetic energy is actually this value here. This is equal to change in kinetic energy rotational. Notice here we have calculated the work done earlier to be 64 joule, and the final kinetic energy, which is equal to the change in kinetic energy, is 64 joule. Therefore, work done is equal to change in kinetic energy.